Hello students, in this video we'll begin our discussion of vector fields. A vector field is a mapping either from R2 to R2 or R2 to R3. Either V maps R2, and I input a two-dimensional vector and output a two-dimensional vector, or V maps R3 to R3. So over here for vector fields, our input is a 2D vector, and our output is a 2D vector for this first example. And over here, our input is a 3D vector, and our output is a 3D vector. There's generalizations of this where you can input two-dimensional vectors, output three-dimensional vectors, but for us, we'll primarily be concerned with inputting two-dimensional, outputting two-dimensional, or inputting three-dimensional, outputting three-dimensional. Let's look at some examples. So here are some examples of 2D vector fields. So these are 2D vector fields. One we'll look at v of xy. So I'm going to input a vector xy. So now I'm thinking about xy as the vector xy. So my input over here is really x I hat plus y j hat. We can think of it as a vector. And I'm going to output the vector. What will my vector output be? The vector output will be negative y I hat plus x j hat. So I take the first component, x, and I move it to the second component. I take the second component, y, and move it to the first component and negate it. So that's an example of a vector field. This one is a particularly useful one. It's a standard type of vector field. I can give another example of a vector field. I could have done something like this. I could have said v of xy was x squared minus y squared I hat plus 2xy j hat. That's another example of a vector field. And so again, our input is exactly the same for both these situations. So those are examples of two-dimensional vector fields. Very special examples of two-dimensional vector fields, but vector fields nonetheless. If we take our first vector field, we can use this to illustrate our plotting convention for vector fields. Our plotting convention is that if I input a point, or a vector xy, if we, for example, were to input v of 1, 1, I would output negative I hat plus j hat. Our convention is that we use this point 1, 1 as the starting point or the initial point of the vector output. So that 1, 1 will be the initial point of the vector output, and this will be the output. So I go to my initial point. My initial point is 1, 1. That is my vector input. I input the vector 1, 1, which would be this vector over here. That would be the vector I input. And then I output a vector that comes from the output of the vector field where the input vector ended. So I'm going to have a negative I and then positive j. So that would go over to the right 1 unit, over to the left 1 unit rather, and then up by 1 unit. So the vector field that we're going to output over here will be this vector like that. So that's our vector output, negative I hat plus j hat. And we do this at every point. One more example I could do, I could plug in the point 1, 0, and that would be my initial point. So I'd start my vector over here, and then the output of that is, well, the x goes into the second slot, so that would be a j hat, and there's no I hat. So over here, the vector field will output a j hat. And we can systematically plot the vector field in this way. If we do one more example of this, if I look at v of, for example, if I go to 0, negative 1, then I go down to 0, negative 1 on my axis. And if I input this, the y is now negative 1, so I'm going to output I hat here. So at this point, I'm going to plot the vector I hat. And so doing this, we can plot the vector field at infinitely many different points. And so we can just continue this procedure by plugging in more and more initial vectors and outputting the corresponding vector point. If we now look at some examples of three-dimensional vector fields, what will we have? So here are some examples of 3D vector fields. We'll do a classical one, which is v of x, y, z. Relatively simple. You input x, y, z, and you output x I hat plus y j hat plus z k hat. In other words, your input vector is immediately output as the same vector. This is called the vector field of position. and this plays an important role in vector calculus, as we'll see later. Oftentimes the vector field of position is written as r of x, y, z, or simply just sometimes as vector r. Okay? Another example of a three-dimensional vector field, let's do one like this. Let's do v of x, y, z. Could be y plus z I hat plus x plus z j hat plus x plus y k hat. There's yet another example of a three-dimensional vector field. I input a three-dimensional x, y, z. That's my input. And now my output is this vector over here. So in general, we can come up with lots of examples of vector fields where there's a three-dimensional input and three-dimensional output. And some of these things happen to have a special sort of structure to them, and we'll study that structure more concretely in the later section. Now, as a note, when you're plotting three-dimensional vector fields, the situation gets even more complicated because not only do you have to plot a vector at each point in space, but now you have to start with the initial point. So if I was to plug in, for example, if I plugged in the point 1, 1, 1 to this vector field, that would be the starting point of my output. The starting point of my output would be at 1, 1, 1, 1, 1, 1. And then I would output what? I'd output 2, 2, 2. So the output of that vector would go along the same direction, and it would go something like that. So then I'd have to plot this vector field at every single point. All the vectors start to coalesce, and it'd be a mess to see. But as long as we can plot a sufficient number of initial vectors to get a sense of what the vector field is doing, we'll be able to get a geometric understanding of what the streamlines will be doing. Thank you very much.